I will explain question number 1. The meaning of technique of differentiation. The meaning of differentiation is a process used to find the rate of change of quantity with respect to another quantity. Some technique of differentiation are: number 1, power rule, d over ds, bracket x power of n equal to nx power of n minus 1. Number 2, product rule, d over dx, uv equal to u dy over dx plus v brackets du over dx. Number 3, Quentin rule, d over dx, u v equal to v brackets du over dx minus u brackets dy over dx over v power of 2. Number 4, chain rule, d over dx, f bracket gx equal to f prime gx multiplied by gfx. Number 5, implicit differentiation, used when y is not written explication in terms of x. The last one is trigonometric differentiation. This technique helps us differentiate different type of function error.
Next, we'll be moving on to question number 2. Find dy over dx for the following function, which is y equal to ln 2 plus x cubed secant 2 minus x. So for this question, we'll be using product rule. So for the first step, we need to find u prime and v prime. As we know in the question, u is equal to ln 2 plus x cubed. For differentiating ln x is equal to 1 over x, that is the formula. So we differentiate the ln, we get 1 over 2 plus x cubed. Then we need to differentiate what's in the bracket. So 3, bring it to forward, we got 3. And then we minus the power, which is 3 minus 1, we get 2. Then we solve, we need to multiply the 2, we get 3x squared equal to 2 plus x cubed. Next, we need to find v prime. V is equal to secant 2 minus x. To differentiate secant, we use the standard differentiation rule. The derivative of secant x is secant x multiplied tangent x. So we got v prime equal to secant 2 minus x multiplied by tangent 2 minus x. Then we also need to differentiate inside the bracket, which is we got negative 1. We multiply all of them, we got negative secant 2 minus x, tangent 2 minus x. Now we know all of the terms, we can substitute inside the product rule. We substitute and we get ln 2 plus x cubed multiply negative secant 2 minus x, tangent 2 minus x, plus secant 2 minus x multiplied by 3x cubed over 2 plus x squared. Then for the final answer, we got secant 2 minus x multiplied by 3x cubed over 2 plus x cubed, negative ln 2 plus x cubed, tangent 2 minus x. So for the next question, B, we need to find dy over dx for the function y equal exponent to the power 3x squared over tangent x. So for this question, we need to use quotient rule because it is division. The quotient rule formula is dy over dx equal to vu prime minus uv prime over v2. First, we find u prime. So we know that u is equal to exponent 3x squared. So we need to differentiate exponent. For differentiating exponent, we first write back exponent 3x squared. Then we need to multiply the inner function, which is 3x squared. We differentiate, we got 6x. Then we multiply the two functions, we got 6x exponent 3x cubed. Next, we need to find v squared. V is tangent x. Then differentiating tangent x is equal to secant 2x. So we got secant 2x. Now we got all of the term, we can just substitute inside the quotient rule. We substitute and we will get exponent 3x squared multiply secant 2x minus tangent x multiply 6x exponent 3x squared over tangent x squared. Then we'll simplify all of them. For the final answer, we will get exponent 3x cubed bracket 6x tangent x minus secant 2x over tangent 2x.
So for question 3, we need to separate it into a different part. So for first part, we need to differentiate cos for e2y minus x cubed. So first, let u equals to e2y minus x cubed. Then we differentiate cos u for the final answer we're going to get is negative 4 cos cube u sin u du dx. So next step, find du dx. For du dx, we are going to use chain rule to differentiate e2y minus x cube. For e2y minus x cube, we are going to differentiate it to become 2e2y dy dx minus 3x squared. And for the final answer, we get negative 4 cos 3 e2y minus x cube sin e2y minus x cube times by 2e2y dy dx minus 3x squared. So for the next part, we are going to differentiate negative ln y square. So d over dx, negative ln y square, differentiate is going to be negative 2 over y dy dx. Next, we are going to differentiate our right hand side, which 4xy. So by using the product rule, we are going to do cross multiplication, and then we get d over dx 4xy equals to 4x dy dx plus 4y. So now we are going to combine all together and expand the equation. So for the second last step, we are going to move all the dy dx terms to one side and all the remaining terms to the other sides. Then we are going to divide both sides by the coefficients of dy dx. In conclusion, by using implicit differentiation, chain rule and product rule, we successfully obtained the derivative of dy dx given by this question.
Question 4, brackets 1 6.03 power of 2 minus 1 over 4 root 1 6.03. First, let fx equal to x power of 2 minus x power of minus 1 over 4. We choose at initial equal to 1 6 because it is close to 1 6.03. Differentiation the function f prime s equal to x 2x plus bracket 1 over 4 x power of minus 5 over 4. Next, substitute x equal to 16, f16 equal to 255.5, f prime 16 equal to 32.0078. Use the linear approximation formula, fx equal to ff initial plus f prime initial bracket x minus of f initial. Substitute x equal to 1 6.03, so f equal to 16.03 equal to 155.5 plus 320078 multiplied 0.03. Therefore, the estimate value is 256.460. That's all. Thank you. The recommendation that we choose is master the calculus hierarchy of rule. When faced with complex functions, like in question 2 and 3, students often struggle with where to start. We recommend adopting a top-down structure analysis before writing down any method. First, identify the outer framework. Determine if the overall expression is fundamental, a product, a quantum, or a composition or a composite function. Require the chain rule. Simplify before differentiation. Whenever possible, use algebra manipulation or log properties before apply calculus rule to dramatically reduce algebra error.
In conclusion, this presentation has demonstrated the fundamental concept and techniques of differentiation in calculus, beginning with the definition of differentiation as a process of determining the rate of change of a function. The presentation progressed through a major differentiation rules, including the power rule, product rule, quotient rule, chain rule, implicit differentiation, and linear approximation. By applying this technique to different types of problems, it became clear that selecting the appropriate rule based on the structure of the function is essential for obtaining accurate resolution. Overall, mastering the hierarchy of differentiation rule, simplifying expression before differentiation, and Practicing a variety of question types are a key to improving problem-solving skills and building a strong foundation in calculus for more advanced mathematical applications.